Hi, and thanks for finding our channel. If you're like us, then you're probably really interested in how the universe actually works. And if you want to learn as much as you possibly can about how the universe works, there's a couple of things you can do. You could go to uni. You could study hard, work for years and years, and eventually come away with that physics degree and try to uncover some mysteries of your own. Or you could do what we did. Find someone who's already done the hard work and ask them what they know. So we sat down with the head of physics at Melbourne University, Professor Raymond Volkas. He's one of Australia's head theoretical particle physicists, so he knows his stuff.
He knows.
We asked him a few questions, and here's how it went. Well, thanks for being here, Ray.
My pleasure.
I suppose one of the main questions I have is what is it like being a scientist in Australia? How does the Australian scientific community add up against the rest of the world?
Well, I think we're very competitive. Obviously, Australia is a modestly sized country. I mean, it's not a tiny country, but it's not a big country either. It's medium-sized. So the proportion of the world's scientific output that comes from Australia is, I can't remember what it is, 1% or 2% or something like that. But, typically, we can argue in many ways that we punch above our weight. And we're very coupled in. So I'm a theoretical particle physicist, and certainly in my field and in many fields of science, it's a very international endeavor. We're publishing in the same journals as everybody else in the world, the top journals in the world. We do a lot of travel. I'm going to France next week, for example. We have international collaborators routinely. Our PhD students get postdocs all over the world. We get international postdocs coming here. We get international students coming here. We have undergraduates and MSc graduates going to other places to do their doctorates. It's a completely, international activity. The big advances that take place in particle physics are worldwide events, like the discovery of the Higgs boson that we had a part in promoting when it happened, and indeed in actually doing. So we are just fully part of this scientific ecosystem that exists on the planet.
Great. I like the way you put it, a collaborative ecosystem that everyone has to talk to each other.
Collaborative and competitive, yes.
Yeah, at the same time.
Some combination of the two, yeah.
So you're the head of physics here at Melbourne Uni.
I am,
so, considering that Melbourne Uni is probably the most reputable uni in Melbourne.
Yes.
In a sense. So you could argue that in Melbourne, you're the guy who understands the most about the universe.
I think that'd be a fair statement. Definitely most in this room.
I think there's a bit of a leap from being the administrative head of of the School of Physics to knowing most about the universe in Melbourne. No, I wouldn't want to claim that.
We'll claim it for you, okay. If you're too humble to. I had a question. Obviously, being a theoretical physicist, use a lot of mathematics to help understand this concept and organise these models that help explain the universe.
Yes.
I want to know from the bottom up is how a mathematical formula is postulated, how it's come up with, and how that leads to eventually going to CERN and going, okay, we can test this. I know it's a very broad question.
It's a very interesting question. There's no way to give a simple answer. I mean, the basic fact is that mathematics has proven to be the best way by far to precisely understand the fundamental laws of physics and hence of the universe. Why that is the case is a mystery. I think it was something that Einstein, for example, was rather taken by. He knew, he was a master of using mathematics to understand the universe, but why it was that worked, he found mysterious.
So would you find that generally you would have a theory, have an idea, and then try to apply the maths to prove this theory, or does it sometimes work the other way around, in which you'll be experimenting with different mathematical models, which in turn answers your question.
Oh, so that's
offers answers that you weren't even looking for, I suppose.
Congratulations, that's a very interesting question. So it can go both ways. So typically, so it can be that you are imagining some new way of understanding a physical system in your head. You're just imagining it. And you're not thinking of it in terms of solving equations, but you're just imagining things about it.
Even it's actually visualize it?
Yeah, it can be visualization. It can be all sorts of things. That would be an interesting topic to discuss in its own right. Not sure I'm the most qualified, but you know, there's a creative. One thing I like to get across about science is it's a strongly creative activity. I don't know. One of the things that irks me, I guess, about the way that the general public sometimes think about science and scientists, and this is maybe comes across a little bit in popular culture, is that somehow we're very dry individuals who you just collect a lot of data and then we work out the truth.
Yeah.
And in fact, it's not like that. I mean, we do collect a lot of data and we do work out the truth, but there's a lot of creativity and imagination that has to go into it, and sometimes there are just blinding flashes of insight that come from nowhere, right?
Yeah.
Which are imaginative leaps, and then you about the way certain physical system or whatever it is you're studying, may actually operate. And then what you do is you take that intuition and you make it precise.
Yeah.
Right, and making it precise in physics means putting it in mathematical form. And then you can work out in great detail what's going on, not just qualitatively or heuristically, but in full quantitative detail. And then you can compare with experiment and see whether your hunch about the way things work is really true. I mean, this is what Einstein did when he invented the theory of general relativity, which is his theory of gravitation, actually. He had a vision for the nature of gravity, based on just one of the most basic things that had been observed about gravity, and he built on that over a period of several years, and eventually constructed this elaborate mathematical theory, general relativity, and it predicted some when you looked at the equations, when you actually solved the equations, right, which is now a very precise thing. He, first of all, could explain a famous anomaly about the orbit of Mercury around the Sun that had been a mystery for some time, and it turned out that his equations completely explained the behavior of Mercury, whereas Newton's law of gravity didn't. So that was an important thing for the theory, but also he predicted new things. He predicted that light would be bent by large masses. So light is bent when if a light beam is passing a star, it gets bent in the gravitational field of the star. So this is a famous prediction of his theory that turned out to be correct. All sorts of things now about gravity that were first known about through solving his equations turn out to be correct. For example, the GPS system that everybody uses now to work out how to get to the supermarket or whatever, that system relies on general relativity in order to work properly, because clocks tick at different rates depending on the strength of the gravitational field, and you have to take that into account. So there you go. It's a process of looking at what the world looks like, then appreciating what you don't understand, and then having some insight about it.
And I suppose mathematics is just an awesome tool.
And then the
for
mathematics,
testing your
mathematics becomes a tool eventually, and you don't really have a physical theory until you've put it in mathematical form, right? At least that's the way it is at the moment. Now, you also asked about the process going the other way.
Yeah.
Sometimes are you just playing around with mathematics, and then you find it has a physical application. Well, that can happen too. I would guess it's rarer than going from physics to the mathematics, but it has happened. So, for example, a famous physicist called Paul Dirac one of the founders of quantum mechanics, he invented something called the Dirac equation, and he was sort of fooling around with mathematics when he did that, and he advocated this approach. What you should do is, he said, play around with elegant mathematical formalisms, and maybe they'll have some relevance to the real world, and sometimes they do, and sometimes they don't.
Maths doesn't lie, though, so it's always a good place to start, right?
Well, it can be a place to start, but I guess you can start wasting your time if what your aim is to do is to explain the real world. You might say, oh, I really love this mathematical structure, let me play with it and see if it has some relevance, for nature. That may be taking a bit of a risk from the point of view of wasting your time, because it may be a nice mathematical object, but doesn't actually help with physics. So there are certainly examples of that. So the interplay between physics and mathematics is very much a two-way street. It goes backwards and forwards.
Mutually supportive.
Mutually supportive. That's right.
Great. So one of probably the biggest question, the question that has plagued the minds of everyone for as long as we know, is the origin of the universe, where it comes from, how did it get here, what's it made of?
Is there only one universe? These questions, they rock us at the core. They're so intriguing when I look out at the night sky. It's amazing that there's. I don't believe in a creator. I believe it's all just there, and it's amazing that it follows these rules, and there's an elegance to it. Uncovering the nature of that is so intriguing. Talking about, I know you study the idea of multiple universes and the idea of string theory relating to multiple universes. Do you have an intuition that our universe is one of many, or it is simply a mathematical model that works so well that you can't deny its implications?
Well, first of all, I don't personally work in that area, but I do know a little bit about it. I'm not an expert in it. Personally speaking, but my personal opinion may not be particularly important, I've always been a bit uncomfortable with this idea of a multiverse being an inevitable consequence of the way we currently understand the universe, because to me it's a huge extrapolation.
I'm glad to hear you say that, because I actually agree. I find it more of a nice philosophical idea rather than something that... Is there anything to actually suggest, anything empirical?
Well, it's almost too hard. It's impossible to make these predictions.
Or
to test these predictions.
Yes, it's by definition to go find a universe that there's outside your own is a little bit difficult to do in a practical sense. But let me tell you why some very smart people do take this seriously, right?
Great.
And the reason is, we are trying to understand the universe that we are living in. We do our best to do that. We get some very precise theories. And then you find that when you push those theories, take them really seriously, push the theories to their limit, you find that they have the consequence that there's a multiverse, meaning that the space-time that we live in and experience is only one portion of a much more complicated structure where there are other kind of universes out there. This is something that is claimed to come about when you combine string theory, which is one of the best candidates we have, well, probably the only candidate we have at the moment for what is sometimes called a theory of everything. In other words, it's a theory of gravity and all the other forces and particles in nature. When you combine that with a cosmological requirement called inflation. So inflation is for which there's a lot of circumstantial evidence, is a period that is thought to have occurred very early after the Big Bang. And in some sense it is the Big Bang. It's a period of exponential expansion of the universe. So exponential means really, really rapid expansion of the universe.
Was it faster than the speed of light? Or,
Yeah, actually the bits of space-time were moving away from each other faster than the speed of light. But the local, anyway, that's another issue. It turns out that when you look at these inflationary theories rigorously, And there isn't just one. There's like a multitude of them, and we don't know which is the correct one yet. It turns out that many of them, not quite all of them, but many of them do predict the existence of a multiverse. Right. So if you believe in inflation and you believe we're using the right equations to describe inflation, those equations, for most inflationary models, have as a consequence, according to the experts in this field, the existence of something called eternal inflation, which gives rise to this multiverse structure. And then string theory comes in and says the following. So string theory admits a very large number of solutions which represent possible universes, if you like. I'm not sure what the current number is, but it's very large. It's either 10 to the 500 or 10 to the 1,000 different possible universes. These are called the string vacua. That's their technical term.
Oh, wow.
But it doesn't matter. Think of each one. These 10 to the 500 or 10 to the 1,000 things are all solutions of the equations of string theory, and those solutions represent possible ways that the universe could be. And the idea is that when you combine this vision of eternal inflation and the multiverse with this string theory fact that there are these 10 to the 500 or so different possible universes, the idea is that inevitably what should happen is that each of the different universes within the multiverse happens to have selected a different solution from string theory. So the next universe along, so to speak, may have completely different laws of nature to this one. Right? It may not be atoms and protons and electrons and photons and so on. Could have completely different laws of physics.
That vastly different these other universes could be.
Some of them are and some of them aren't. So there's a whole range of possibilities. So that's where the modern multiverse, modern multiverse is what you get when you combine that aspect of string theory with inflationary cosmology. You get this bubble-like structure of different universes with different laws of nature in each of them.
Is that like the bubbles within Swiss cheese type theory? Is that referred to?
Because it's such a multi-dimensional space.
Yeah.
It's not possible for a human to really visualize it. But if you're going to visualize it, that's about the only way you can do it.
We try, don't we, as humans?
Well, we can't. Physicists can't visualize it either, but can solve equations.
The model that we've come across recently that sparked our interest has been that of, we recently read a book by Lawrence Krauss, Universe from Nothing.
Right.
And I'd love to talk to you about this idea and what you think of it, the idea that a universe can spontaneously rise from nothingness, so to speak.
Yeah. So again, I'm not an expert on this, but the idea is that there are both positive and negative contributions to energy. So it could be that the energy of the universe, as I understand it, as a whole, is zero.
Zero-sum energy.
And obviously, there's a lot of phenomena in the universe that have positive energy, but then there's gravitational energy associated with the universe as a whole, which can be negative, and the two kind of exactly cancel out. So the idea is that from a state of zero energy, through the action of quantum mechanics, which allows things to happen spontaneously, fluctuations they're called, one can get a universe like we see, because although it doesn't seem like it at first sight, actually the total energy is zero.
Right.
So, I think it's possible. Is it really true? I have no idea, but it certainly makes sense.
Right. So what model would you subscribe to mostly when talking about origins of universe?
Or do you rather sit on the fence and just keep testing different theories?
I guess I do sit on the fence. It's I think we don't know the origin of the universe yet. I don't know how long it will take us to find it out. Maybe we'll never find it out. I don't want to leap to conclusions about what the origin of the universe is. I think it's fine to explore possibilities. But, when you're doing science and you have a number of different possibilities to explain something, ultimately you want observations or experiment to tell you which of those possibilities, if any, is correct. So I don't know how observationally, experimentally we'll get to the bottom of the origin of the universe and how long that will take. It could take a long time. So I personally, when I'm doing science, I prefer to stick closer to things that can be experimentally tested. I mean, I love speculations. I mean, I speculate for a living, but there are degrees of speculation, right? And yeah, I think experimental testability is very important. I'm not saying these things aren't in principle testable, right? But you know, sometimes they can be very, very hard to test in practice. So, for example, you know, I believe in black holes, that they exist, and there's a lot of good evidence that they're plentiful in the universe. But we can't do experiments on a black hole because we don't have one around,
Exactly.
you know. So all we can do is observe astrophysical systems that give the distinct impression that they have black holes embedded within them, and do our best there. So we can do something there observationally, but it's not as good as actually having a black hole in the lab. Well, but you need something, you know.
For it to be considered knowledge, you essentially need an observation to be made somewhere to go, okay, we can really put this off the theoretical shelf into the...
Well, because this is the whole point of science, is to you know, it's to validate your imagined physical laws against reality. And you know, many beautiful ideas have died because, you know, it's still a beautiful idea, but it just didn't happen to be used by Mother Nature. You know, so.
I'm actually curious about that. What's it like when you spend? I imagine you spend many years sometimes focusing on one particular area of your field. What happens when that is proven? Has that ever happened to you where you've worked on something for so long and then it is proven wrong? Is it easy to bite the bullet and accept that, okay, wow, I've dedicated a lot of time to something that now is proven to be
Wrong.
Yeah,
look, it has happened. I have worked on things that are proven to be wrong.
Or do you just simply embrace it as that's the nature of science?
Well, it is you have to be mature about it. So, I mean, I personally, therefore, have worked on a range of different things, knowing that if I put all of my energies into one speculation... So I should explain that what I'm interested in research is uncovering new particles, new forces, new laws of nature. This is called beyond the standard model physics. So that's what I like to do, and it's inherently speculative because you first have to imagine what new physics could be like, you know, what the dark matter could be, for example. And then you write down a theory, and then you examine its consequences, and you work out how to test the theory. So it's speculative. So what do? Do you explore a range of different speculations, knowing that any one speculation has very little chance of being correct? Or do you spend a lot of time deciding upon criteria that you think make a particular kind of speculation extremely compelling, and then devote all your energies to exploring that? So you're putting all your eggs in one basket, right? So if you're right, you're really right. You know.
I suppose ideally you'd want more and more people putting their eggs in different baskets. So more people having their own baskets.
I absolutely think that there should be a wide spectrum of different ideas explored all over the planet, so that we make sure that someone out there is right, and then we will congratulate them and give them a first-class ticket to Stockholm and other things like that. I'm for plurality of idea explorations in science.
Definitely.
Not everyone is. You know, some people do have pet ideas. And argue for them.
You become biased very strongly.
Quite aggressively. And if they're so this can lead to a sociological problem. Because if a very powerful physicist thinks that a particular line of investigation is extremely compelling for very good reasons, and promotes that aggressively around the world, it can become a dominant paradigm. And the problem is it's a speculation still,
Yeah.
right? And if it's wrong, if it proves to be wrong, then, and a huge number of people have worked on it.
Taken on for
A
that.
lot of funding, yeah.
Yeah. So, they would argue, well, but this is so compelling, we really must focus our efforts in this area and not be diluted by exploring every single crazy idea. But I'm more of the view that there should be a plurality of exploratory paths because at the end it's somebody's theoretical prejudice, that tells you, I think this is a really compelling way forward. It's different if there's an experimental anomaly. So like the existence of dark matter. Mm-hmm. There's no doubt that dark matter exists, right? The evidence is overwhelming. So we know that's a problem, right? So devoting a lot of energy to studying the nature of dark matter is completely rational and justified, and I would fund that. Within that, though, you can have different kinds of candidates for dark matter. Dark matter is actually notorious because we know so little about it. We know it exists, but as far as its properties go, we know certain basic things, but otherwise we're sort of ignorant. So within the field of what could be the dark matter, there are many different directions you could go. And again, if you just go along one direction all the time, you can run into trouble. If you're right, great, you'll be extraordinarily happy. But if you're wrong, you've really wasted your time. Wasting your time is probably is overstating it. You'll always learn.
We should always cast our net wide.
Well, you'll always learn things, even from theories that have proven to be wrong. I mean, not wrong in the sense that you couldn't solve equations properly, but wrong because nature didn't happen to make use of that idea. Right?
That's valuable information, though. If we know that this is wrong, it's not worth considering anymore.
Of course,
shift our attention elsewhere.
That's right. Science sifts these things out. So yes, it's valuable information. But of course, from a personal point of view, it's more satisfying to be part of a part of developing, a paradigm or a theory that turns out to be correct. Rather than having helped to eliminate 100 wrong ideas, but even wrong ideas, you think stuff can be learned from them. They're not. It's not useless.
But even ideas that might initially be wrong, as Einstein once said that his cosmological constant was the biggest blunder of his career. Yeah. And now is it that we look back on we look on dark energy and it seems to be some kind of constant.
Yes.
So I mean, he assumed that he was wrong then, but he could be right in a way that he didn't think.
Yes. Well, he didn't believe his equations. So his equations told him that the universe is either expanding or contracting, but it's not static, Right. And at the time, and this was 100 years ago now.
So it was pre-Big Bang idea.
Yeah, pre-Hubble.
Yeah.
Of course.
You look at the night sky, and apart from the odd meteor and the fact that the planets move around
seems pretty static.
It seems pretty static. So it was hard for him to accept that his equations, which were so beautiful to him and seemed so right, were predicting a non-static universe. And so he fudged. He put a term in the equation that allowed him to have a static universe. And this term was the cosmological constant, which I think he considered the blunder to be insistent that he should ad hocly modify his theory to meet a prejudice. So he had a prejudice that the universe should be static. So see, here he was a genius, and that was a wrong prejudice. So if he'd only believed his own theory...
Yeah, it's funny that his own mathematics worked, and...
I suppose that's interesting. Like, 100 years from now, we might be looking at things that have been written off as improbable or implausible now, and they may be fundamental in the science of the future.
Yeah, things probably can come back into relevance. I'm not sure I can come up with an example on the fly, but I mean, all knowledge is in some sense useful. Yeah, sure.
So I'd love to go back to dark matter, what we were talking about before. What would you say? Is there any experiments that are going on right now in trying to detect dark matter that pretty solid?
Do you think it will be the Large Hadron Collider that will happen to come across one of these weak, massive particles?
So, this is a very important topic. So as I said before, dark matter is notorious for being, at this point, able to be a lot of different kinds of particle, or even more than one kind of particle. So we just don't know. So again, here plurality is important. Since there are many possibilities, we need to, for the moment, do a range of experimental explorations and see which one comes up trumps. It could be the Large Hadron Collider, but it may not be. If dark matter is a certain kind of particle, then the LHC may be the best place to find it. But there are plenty of other kinds of dark matter which the LHC would not be able to find. And other experiments need to be designed to do that. And they have been, and they are being done. So there are these things called dark matter direct detection experiments, of which there are several around the world. So these are just detectors. These are instruments which are designed to detect particles. So what they do is just build one of these detectors and instrument it and look at the detector. Put the detector deep down a mine or under a very big mountain. This is in order to shield it from cosmic rays.
Yep.
And then what they look at, so what the detector is designed to be sensitive to recoiling nuclei. So in every atom there's this nucleus right in the center made of protons and neutrons. The idea is that a dark matter particle may come along, collide with a nucleus, and then the nucleus picks up energy. Right?
So you're not
recoils.
trying to detect the actual dark matter particle, but rather what it's doing to the
effects.
nucleus.
Of course, because the dark matter particle you can only see through its effects. So what you're doing is you're waiting for a nucleus to suddenly pick up kinetic energy for no apparent reason, right? So it's like you have in the room an apple, right? And you do nothing to the apple, and suddenly it flies off the table, right? So you would say something hit that apple. All right. So now imagine that apple is the nucleus inside a detector, and suddenly you see it shoot off, and you keep seeing nuclei shoot off occasionally. You would say, well, something is bombarding that nucleus. It's something that's very weakly interacting, that can get under a huge mountain or down a kilometer or two under the earth in a mine. So you would say this looks awfully lot like dark matter. So that's what direct detection experiments try to do. And there are several around the world. There are even some that claim to have detected dark matter already.
Oh, big claim.
Yeah. So and this has been going on for several years. Controversial. The experiments are not universally believed, or the interpretation of the experiments as the detection of dark matter is not universally believed. And there are experiments that contradict other experiments and so on. It's a confusing but exciting story at the moment. So dark matter is something is I think one of the most important areas in fundamental physics and indeed in fundamental science at the moment, and is under very active consideration both theoretically and experimentally, and is one to watch. And there could be a breakthrough. It has the potential for a breakthrough. Over a reasonable time frame. Yeah.
Do you think the dark matter particles, do you think their nature is of particles similar to ones that we know, or they will have the complete, or that they're rather different than what we know? I know they're non-luminous, so we can't shed a light on them in one sense, but do you think they're completely different to normal matter?
My prejudice is that there isn't just one dark matter particle, but there's a whole set of particles which interact with each other, just like ordinary particles like electrons, protons, and neutrons interact with each other. I think there's another kind of system like that, a set of particles all interacting with each other.
They just don't interact with light,
but they don't
detect them.
Exactly. They interact with ordinary matter gravitationally, because that's how we've detected dark matter. But they certainly don't interact with light, at least certainly not very much. They can interact a little bit, but very, very, very weakly.
Which makes it very hard to detect.
Well, that's right.
They're flying around this route, flying through us at the moment. They just...
Yep.
So I find it... all the questions in physics seem in some way to go back to gravity. And it's funny how these particles... they adhere to gravity, the force of gravity, but not the other fundamental forces. What makes gravity such an interesting and difficult aspect of the physical universe?
So what's different about gravity is what causes a gravitational field is basically mass and energy. And everything has mass and energy, or certainly energy, including dark matter. Dark matter has mass and it has energy, so it will create a gravitational field. So the universality, and also there's no anti-gravity, so you can't screen gravity. So, you know, the electromagnetic force is much, much stronger than gravity. But there are positive charges and negative charges. And when they get together, they screen each other, and you have a neutral, you know.
So there's no negative gravity.
There's no anti-gravity.
So there's no antiparticle to the gravitron, so to speak.
Well, not so much the graviton, but say the proton, say an electron, and its antiparticle, the positron.
They both still have
a
positive gravity.
Exactly, they both have a positive gravity. So gravity is always attractive, and you can't screen it, and it's universal. It couples to all forms of energy. That's why gravity is important for large-scale physics like cosmology, because it can't be screened. It's a very, very weak force. It's the weakest of the four forces of nature that we've so far discovered, many times weaker than the others, but it's very long-ranged, and it builds up as you get more and more mass and energy. The gravitational field keeps getting bigger and bigger and bigger. And because it couples to everything, you do have the potential through gravity to find other things, like dark matter.
So the fact that it is linked to everything makes it good for observation, I suppose.
It does. It makes it good for, I guess, discovering new types of particles, at least if they're around in great numbers, right? If they're around in minute quantities, then gravity is way too weak to find them. But this dark matter, by the way, there's 5 times as much of it in terms of mass per unit volume as there is ordinary matter.
Am I right to say it makes up approximately 27% of the entire universe that we know?
Yeah, the ratio of ordinary matter to dark matter is about 1 to 5, and then. But then most of the energy density in the universe today is in this dark energy, this cosmological constant.
Yes.
And it's only about 30% or so of the universe that is in the form of matter, and most of that is dark matter. Yeah. So ordinary atoms is just like 4 or 5% of the.
And we thought it was universe. Pretty much everything not so long ago.
Yeah. So, we can say that we really don't understand 95% of the energy that's in the universe, which is, you can say, well, that's bad, but I find that exciting. It gives us something to do.
It must be exciting for you to have your finger on the pulse of these kind of ideas. Would you say that the speculative nature of your work, does it allow you to maintain the excitement that I imagine you would have got into this field based on the excitement from uncovering the truth of the nature of reality, right?
Well,
it allows you to maintain that and still stay excited and be, want to discuss these ideas. Obviously, you've taken the time out to talk to us. You enjoy discussing these.
Yeah. Well, I love thinking about, new laws of nature, new particles. I think the dark matter problem is really fascinating. I remember as a high school kid in the 70s. I used to read, news about advances. I was particularly interested in physics, so news about advances in physics, and a lot was happening in the 70s. A lot of new particles are being discovered, and one in particular was the discovery of a particle that's now called the J psi. It's a funny name, and that caused huge excitement. It happened in the mid 70s, and it was actually ultimately the discovery of a new kind of quark, the charm quark. And just reading about the way that happened, there was a competition between 2 experimental groups, on the west and the east coasts of the US.
Which is already a rivalry. So.
The Crips and Bloods of the physics world.
And the story was that many physicists told the people who are running the experiment, "You're wasting your time. You're not going to find anything when you look in this energy range." but they insisted on looking, and then they found this amazing phenomenon, So it was like, hey, the underdog won. There was a bit of luck involved, but and then just the fact that this was unexpected and created such a stir and really provided a massive insight into the way elementary particles were behaving. That sort of thing struck me, and I guess I wanted to be involved with that.
Awesome.
Problem is now it can be a long time between drinks in terms of major experimental discoveries. So the Higgs discovery a couple of years ago was brilliant. That was just great.
Yeah, of course.
I mean, we had such an amazing experience here being part of the announcement through this conference we were running in Melbourne. And the outpouring of media interest after that for 2 days,
Definitely.
all over the world, headlines all over the world, that's just amazing.
That's it.
There's always new discoveries to be made.
Yeah.
That's it. Well, look, I know you got to shoot off
Yeah.
pretty soon. Thanks for taking the time to talk to us.
My
But
pleasure.
also, look, we'll leave you with one question.
We wanted to know if you could have, or someone could whisper in your ear an answer to one of the questions that you're working on, what would it be?
Well, not even that you're working on. That broad.
Yeah,
make it
if you
broad
could
than
have
that.
one answer to any of the questions in physics, like you could know that was the certain truth, what would it be? Or would you rather not ask and discover it yourself?
I would have to say what the dark matter is.
Yeah, that is the big one in the world, isn't it? I suppose at the moment.
It is, in my opinion. Some people would say dark energy, but I'm personally more interested in dark matter.
Do you think we'll know in our lifetime?
I think there's a good chance. There's no
Yeah.
certainty, of course, but I think there's a good chance. Yeah, sure.
Good one.
Well, hopefully you guys get to it and we can all sit back and enjoy your
Oh,
findings.
man, I'm sure we
We'll
could
do
talk
our
about
best.
we can talk about this for hours. But look, we appreciate you taking
Yeah,
the time.
thank you
out
so
to-
much, Ray.
to
My
chat with
pleasure.
us. So thanks heaps, Ray.
Thank you.
That was pretty good.
That went really well.
Yeah, nice guy too. Hey.
Very nice, very smart.
Yeah, knows his stuff. Knows his stuff. So would you like that?
I did.
Yeah, but would you like it if there was
Yeah,
a button per se that you could
I'd like
you could,
it, yeah.
would you subscribe to it?
I would definitely subscribe.
Interesting. Something to think about.
Something to ponder. PonderCast.
Nice.
Yeah. We're PonderCast. Thank you for having us.